Pluto is a distant and subtle, more humble planet that was once a piece of our close-by planetary assembly. However, advancing and disturbing announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a dazzling exposure. They suggested that this icy world is on a potential collision course with Neptune. But how could this really happen, and what might be the outcomes of such a titanic event? Are we witnessing a baffling and remarkable quirk? Or is there something more to this impending cosmic collision? Join us as we explore the potential outcomes of a Pluto-Neptune impact. Pluto, a former planet that was later reclassified as a dwarf planet, remains a subject of interest and focus in the vast universe. According to recent assessments by leading scientists, Pluto's orbit is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a possible dangerous collision between these two celestial bodies, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is characterized by its highly eccentric shape, differing greatly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more extraordinary is its inclination, which is tilted at 17 degrees to the ecliptic plane. The way Pluto follows its path is far more extreme compared to other planets. This inclination and irregularity add layers of complexity to its orbital arrangement. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect based on their positions in the planetary system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers attempted to understand its unique path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out with its steep inclination and eccentric shape. The mystery deepened with the realization that Pluto's orbit crosses Neptune's. The stability of Pluto's orbit, despite these complexities, is a testament to the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects, such as Pluto, Neptune, and the Sun, move and influence each other through gravity. It's like trying to predict their future positions based on their starting points and how they pull on one another. In Pluto's case, this problem demonstrates how its orbit, Neptune's orbit, and the Sun's gravitational pull interact in a highly complex way. The terms non-synchronous libration and orbital precession, along with the VZK oscillation, are crucial for understanding this puzzle. According to astrophysicists, what keeps all planets in their orbits is non-synchronous libration. In Pluto and Neptune's case, this means that when Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune. This spatial separation is critical in preventing their orbits from merging. Orbital precession, on the other hand, refers to the vertical movement of a celestial body within its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, adding another layer of protection against potential collisions. Another key factor in this situation is the VZK oscillation, named after researchers Zelkai and others who studied how objects move in space. This concept explains how three celestial bodies, Pluto, Neptune, and the Sun, gravitationally interact and influence each other's movements. In Pluto's case, the VZK oscillation helps us understand why its orbit near the Sun is so irregular. Despite Pluto's path appearing unpredictable, this oscillation helps keep it moving smoothly over long periods. The VZK oscillation reveals that, although things in space may seem chaotic, certain patterns and rules maintain order and stability. These factors ensure that Pluto's orbit remains stable, preventing it from colliding with Neptune or drifting off course. This three-body problem is fundamental to understanding how planetary orbits evolve due to gravitational interactions. Studying this problem helps scientists learn more about Pluto, our solar system, and even distant exoplanets and their stars. Numerical simulations conducted in the late 1980s revealed that, despite these stabilizing properties, Pluto's orbit is actually unstable. Minor deviations in initial conditions can lead to massive differences over thousands of years. However, these peculiarities in Pluto's orbit have been found to maintain stability over incredibly long timescales. Monitoring these orbital changes has been crucial. Later automated assessments have helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship helps maintain Pluto's orbital stability. However, Neptune isn't the only planet at play. Jupiter's gravity also plays a major role in stabilizing Pluto's orbit, and Saturn contributes as well. These studies show that Jupiter's immense gravity is strong enough to keep Pluto on a consistent path for a long time. So, perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto continues moving safely through space without running into trouble. These orbital quirks are fundamental in maintaining order and stability in the solar system. Without these mechanisms, the solar system as we know it would be a much more chaotic place. If these stabilizing forces did not exist, celestial bodies like Pluto could collide with others or be ejected from their orbits, triggering a chain reaction affecting other planetary bodies. Understanding Pluto's orbit is crucial, especially with discussions about its potential future collision with Neptune. The case of Pluto demonstrates how even the most seemingly unstable orbits can reach a state of harmony through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and research to better understand our place in the universe. Studying the depths of space often leads us to confront the unpredictable nature of celestial bodies. Furthermore, Pluto's orbit is a perfect example of orbital chaos, which refers to the extreme sensitivity of a celestial body's orbit to its initial conditions. This is clearly illustrated in Pluto's case. Even slight changes in Pluto's position or velocity can significantly alter its long-term orbit. Computational models have been invaluable in helping scientists understand how Pluto moves in space. Despite having stabilizing mechanisms like non-synchronous libration and orbital precession, Pluto's orbit can still be irregular and unpredictable. Even a tiny difference in Pluto's starting position or speed can result in a completely different orbit after a few years. However, over very long periods, billions of years, Pluto's orbit remains stable. This essentially means that Pluto's journey around the Sun follows a kind of order, even though it may seem chaotic at first glance. Predicting celestial events, especially when dealing with irregular orbits like Pluto's, is an immense challenge. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainties. While mathematical models provide powerful tools for understanding and predicting the future paths of celestial bodies, they also highlight the limitations of our predictive capabilities. These models rely heavily on the accuracy of initial conditions, and any small error can lead to vastly different outcomes, making precise predictions a daunting task. Additionally, the chaotic nature of planetary orbits like Pluto's reminds us of the ever-changing and dynamic nature of the universe. While we have made tremendous strides in understanding space, Pluto's case reminds us of how much remains unknown about our solar system. Understanding the gravitational influences of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how each planet's presence and position can significantly impact the stability and trajectory of other celestial bodies. While leading astrophysicists have recently raised concerns about a possible Pluto-Neptune collision, ongoing research will continue to refine our understanding of this cosmic dance to Pluto's orbit. External forces from beyond our solar system could also play a role. These include passing stars, galactic tides, and even potential encounters with massive interstellar objects. Over long timescales, millions or even billions of years, such gravitational influences could cause subtle perturbations in Pluto's trajectory, possibly shifting it into a new orbital pattern. One such external influence is the Oort cloud, a vast region of icy bodies surrounding the solar system. If a large object from the Oort cloud were to be perturbed and sent inward, it could interact gravitationally with Pluto and other Kuiper belt objects, leading to minor but cumulative orbital adjustments. Additionally, as the solar system orbits the Milky Way, it encounters varying gravitational forces from the galaxy itself. These galactic tides can gradually influence the orbits of distant bodies, including Pluto, potentially pushing it into a slightly different path over extremely long periods. However, for any significant change in Pluto's orbit to pose a real risk of collision with Neptune, a major gravitational disruption would need to occur, one that offsets the stabilizing effects of the current resonant orbit. So far, all simulations suggest that Pluto remains in a relatively stable configuration, thanks to the intricate interplay of gravitational forces among the giant planets. In conclusion, while the idea of a Pluto-Neptune collision is intriguing and makes for an exciting cosmic scenario, it remains highly unlikely. The well-established 3:2 resonance, combined with the gravitational influences of Jupiter and Saturn, acts as a safeguard against such an event. Any potential changes in Pluto's trajectory would likely occur on timescales far beyond human observation, making it a fascinating but distant possibility in the grand scheme of celestial mechanics. For now, Pluto continues its unique and eccentric journey around the Sun, reminding us of the complexity and dynamism of our solar system. Whether future discoveries will challenge our current understanding remains an open question, one that keeps astronomers and astrophysicists eagerly observing the cosmos.